So we're diving into some seriously cool stuff this time, supernovae and those crazy little particles, the neutrinos, right? Sounds like a recipe for, like, the ultimate cosmic light show.
Yeah, it's a really wild area of research, and you've sent over a ton of interesting papers about it. It seems like you're really into, like, the guts of how a supernova actually works, how neutrinos behave, and how these, like, almost invisible particles might actually hold the key to some of the biggest mysteries in the universe.
It's like trying to understand a fireworks show, but instead of watching the explosions, we're, like, collecting the smoke and trying to piece it back together.
That's actually a really good analogy. We can't directly see what's happening in the core of a supernova, but neutrinos can. They escape and, like, carry information about those extreme conditions out into the universe.
Yeah. So before we get too deep into the whole neutrino thing, let's set the stage. When we say supernova, what are we really talking about?
Well, imagine a star way bigger than our sun, like running out of fuel. And without that outward pressure from nuclear fusion, gravity takes over, right? And the star's core collapses, like, incredibly fast.
And that's when things get really crazy, right?
Oh, yeah. That collapse triggers a shock wave that blasts through the star, just tearing it apart, and boom, that's your supernova. It's just this massive explosion, a bright, blinding release of energy.
We're not just talking about a little sparkler here, are we? This is some serious cosmic firepower.
No kidding. For a short time, a supernova can outshine an entire galaxy. It's kind of hard to wrap your head around that kind of energy.
Okay, so where do neutrinos fit into all of this? They seem kind of, well, subtle compared to a massive star exploding.
Right. Neutrinos are subatomic particles. They're incredibly tiny, like almost no mass, and they barely interact with anything, which makes them incredibly hard to detect.
So they're like the ninjas of the particle world, sneaking through everything without leaving a trace.
Yeah, exactly. And because they interact so weakly with other stuff, they basically escape the supernova core super fast, carrying all this info about what happened.
So they're like little messengers from a war zone, carrying secrets from the heart of the explosion.
Precisely. By studying these neutrinos, we can actually see into the core of the supernova in a way that's impossible with just light.
What kind of secrets are we talking about? Give me an example.
Well, there was this supernova back in 1987, SN 1987A, and it was the closest one we had observed in centuries. Scientists only managed to catch about 20 neutrinos from that event, but those 20 neutrinos, that tiny little blip, totally changed our understanding of how supernovae work.
Only 20. Talk about making the most of your data.
Right. It really showed us that these neutrinos are the key. Before that, we thought most of the energy from a supernova was carried away by this shock wave. But the neutrinos told a different story. Turns out a huge amount of the energy is carried away by these little particles.
Okay, so if neutrinos are like chapters in this supernova story, how do we even begin to read them?
That's where this idea of 4 epochs of supernova neutrinos comes in. Imagine it like a timeline of the supernova, and each epoch has distinct neutrino activity.
Okay, so let's break down this timeline. What's the first epoch?
The first part is the pre-supernova phase. This is before the star actually explodes, when it's basically on its deathbed. But even then, it's emitting way more energy in neutrinos than in light.
So it's like whispering secrets before it goes out with a bang.
Exactly. These whispers, mostly electron neutrinos and their antimatter counterparts, give us clues about what's going on inside the core just before it collapses.
And then what? What's next on the supernova neutrino timeline?
Next comes the collapse epoch, which is super short but intense. When the core can't hold itself up anymore, it collapses in like a fraction of a second. And that releases this enormous burst of neutrinos, starting with electron neutrinos mainly, but then quickly becoming this mix of all the flavors.
Okay, it's starting to see how this gets complicated. The collapse, neutrinos bursting out. What happens after that?
Well, things get kind of messy. That's when you get the accretion phase. The collapsed core, it forms this super dense object called a proto-neutron star, and all the surrounding material falls onto it. And that infalling matter, that's what releases this massive amount of energy, mostly as neutrinos.
So it's like this proto-neutron star is having a cosmic feast, gobbling up matter and burping out neutrinos.
It's a very energetic feast, for sure. And the kind of neutrinos emitted, their energies, how long this phase lasts, it all depends on what the original star's core was made of, whether it had lots of oxygen, neon, magnesium, or mostly iron.
So even in their death, stars have their own unique style.
Yeah, and we can actually use those unique fingerprints encoded in the neutrinos to learn about what kind of star exploded and what kind of object it left behind. Like, was it a neutron star, or maybe even a black hole?
This is blowing my mind a little. Okay, so we've got this pre-supernova phase, the collapse, the accretion disk. there's one more epoch, right? What happens in the grand finale of the supernova neutrino show?
The last act is the cooling phase. And as you might guess, that's when the protoneutron star cools down. It releases its remaining energy, mainly through, you guessed it, neutrinos. And this phase can actually go on for tens of seconds.
Wow. So this whole time, these neutrinos are giving us a front row seat to the action.
Exactly. But here's the really wild part. These neutrinos, they don't just travel in a straight line. They actually change their identities, their flavors, as they go through space and matter. It's almost like a cosmic magic trick.
Whoa, wait a minute. Neutrinos changing identities. Tell me more about this whole flavor-changing thing. But, maybe we should save that for part 2. Don't want to overload everyone with too much cosmic excitement at once. Okay, so last time we were talking about how neutrinos can, change their identities as they travel through space. This flavor-changing thing, right? It's blowing my mind a little.
Yeah, it's a pretty wild concept. It's called neutrino flavor oscillation. Basically, you've got these 3 flavors of neutrinos, electron, muon, and tau, and they can actually, transform from one to another as they travel.
So it's not just that they're hard to pin down because they're so small and barely interact with anything. They're also out there changing costumes on us.
Kind of, yeah. So an electron neutrino that's emitted from a supernova core, by the time it gets to Earth, it could be a tau neutrino. It's changed identities along the way.
Okay, that's just too cool.
Yeah.
But what makes them decide to switch? Is it random?
Not exactly. This oscillation thing, it depends on a few things. The neutrino's energy, how far it's traveled, and even the density of the stuff it's passing through. It's called the MSW effect.
Okay, you lost me a little bit there. MSW effect.
Yeah, it's named after the physicists who figured it out, but basically it means that, even the environment a neutrino travels through can affect how it oscillates.
Wow. So we're trying to track these tiny things that barely interact with anything, and they're changing flavors depending on where they are and what they're near.
You're getting it, but there's another layer to it too. You see, for a long time, scientists were missing this one key piece of the puzzle, something called the mixing angle 13.
Mixing angle. Sounds intense.
It's a crucial factor in figuring out how these neutrinos oscillate, especially when they're in these crazy dense environments like a supernova.
So we were missing a piece of the puzzle, and without it, we couldn't read the messages the neutrinos were carrying.
Basically, we had the book, but there was a page ripped out. But thankfully, some recent experiments nailed down the value of this angle, 13, which completely revolutionized how we study these supernova neutrinos.
Okay, so we're starting to figure out these flavor oscillations, but I gotta be honest, trying to actually track these things through a supernova just sounds insanely hard. Imagine trying to follow a feather in a tornado.
Man, that's a great way to put it. It's super chaotic. You've got the shock wave, all this churning matter, these intense magnetic fields.
All messing with the neutrinos and how they're changing.
Exactly. It's basically a neutrino mosh pit in there. They're so densely packed in a supernova that they can actually, bump into each other and mess with each other's oscillations, too.
Wait, seriously? So it's not just, random chance. It's also that they're bumping into each other, and that can cause a flavor change.
Yeah. It's called neutrino self-interaction. They're influencing each other.
So it's this whole chaotic dance, and we're trying to understand the steps.
And that makes it even harder to model, right? You've got all these factors, matter effects, crazy turbulence, neutrinos interacting with each other. It's a huge challenge.
So with all that going on, how on earth do scientists even try to detect these things?
It takes a lot of creativity. But there are some pretty cool neutrino detectors around the world, each designed to capture these, super faint signals.
Yeah, because we're talking about catching these little ghost particles that barely interact with anything, right? What kind of tech are we talking about?
One common type is the water Cherenkov detector. Picture this huge tank of ultra-pure water surrounded by all these crazy, sensitive light detectors.
Okay, I'm picturing it. Big tank of water. What happens next?
So when a neutrino hits a water molecule, right, it can create this charged particle that can actually move faster than light. Well, faster than light can travel in water anyway.
Hold up, faster than light. Isn't that, against the rules?
It seems that way. But remember, nothing travels faster than light in a vacuum. But in a medium, like water, light actually slows down. So these particles, they can briefly go faster than the light around them.
Okay, so we're not breaking the universe here.
Exactly, haha. But when that happens, when these particles break the speed limit, they create this kind of shock wave of light called Cherenkov radiation.
Cherenkov radiation. So this light is what the detectors pick up.
You got it. And these detectors are so sensitive they can pick up these teeny tiny flashes of light from like miles away.
Wow. So it's like we built these gigantic, super sensitive cameras to catch neutrinos in the act?
Pretty much. But water Cherenkov detectors are just one type. Another one uses liquid argon.
Okay, liquid argon, even more sci-fi sounding. How does that work?
It's similar to the water ones. A neutrino interacts, creates charged particles, but this time these particles ionize argon atoms. And we use an electric field to gather these charged particles up, which creates a signal we can detect.
So we've got these giant tanks of water, giant tanks of liquid argon. Are there any other, like, neutrino traps we use?
There's one more: liquid scintillator detectors.
Liquid what now?
It's basically a tank filled with this special liquid that, when a charged particle passes through it, it lights up. This kind of detector is really good at picking up electron antineutrinos, which is key for this whole supernova neutrino thing.
Okay, so we've got water, we've got argon, we've got this liquid that lights up. Sounds like we're taking this neutrino hunting seriously. But just catching them isn't enough, right? We have to figure out what they're telling us.
Absolutely. That's where SNUWPY comes in. It's this software that lets scientists simulate supernova neutrino signals and how we detect them here on Earth.
So it's like a supernova simulator. We can see what kind of signals we'd expect to see with different kinds of supernovae.
Exactly. Researchers can use it to model all kinds of different scenarios, different types of supernovae, different neutrino flavors, how they change on the way here. It's really amazing.
So we're using SNUPY to bridge the gap between what we think is happening and what we're actually seeing in the detectors.
Yes. And it helps us refine our models, test different theories, and hopefully unlock more of the secrets these neutrinos hold.
This is all just incredible. We've covered so much, but there's this one thing you mentioned earlier, this SASI thing that Ice Cube can detect. Can you refresh my memory? What is that exactly?
Oh, right. SAS-I. It stands for Standing Accretion Shock Instability. And it's this really cool phenomenon that gives us this window into what happens right after a star's core collapses.
Okay, break it down for me. What happens?
Well, you've got the shock wave that's supposed to, like, explode the star, right? Sometimes it stalls.
Wait, really? What do you mean stalls?
It's like it hits this wall and can't push through. And that's where SASI comes in. It's basically this oscillation of the shock wave, and scientists think it's critical for getting the whole explosion going again.
So it's like the shock wave needs a little boost, a jump start.
Yeah, exactly. And these oscillations, they actually create these fluctuations in the neutrino signal, and detectors like Ice Cube, which is down in Antarctica, they can pick up on those fluctuations.
So we're talking about detecting these subtle changes in the neutrino signal from an exploding star that's like millions of light years away.
It really is incredible when you think about it. But even with these amazing detectors and tools like SNUPPI, we still have so many questions.
There's still more to learn.
Oh, tons. Like, take turbulence, for example. We know it messes with neutrino oscillations, but we still don't know exactly how.
So we need even better models to really decipher the messages they're carrying.
Exactly. And there's also the fact that these supernova explosions, they're not perfectly symmetrical. They've got all these weird bumps and wiggles, even jets of material shooting out.
Wild. So it's a lot more complex than just like kaboom, everything explodes outward in a perfect sphere.
Yeah, we're realizing it's much more chaotic than we initially thought.
So what are some of the big questions then? What are we hoping to learn from all of this?
Well, one of the biggest ones is whether supernovae can actually tell us about physics beyond the standard model.
Whoa. All right, we're getting really deep now. Beyond the standard model, that's some next-level physics stuff.
It is. And some physicists believe that these supernovae, these incredibly extreme environments, might hold the key to understanding these big mysteries. Like, maybe we'll even find evidence for new particles we never even knew existed before.
It's like we're using these exploding stars as giant laboratories to study the fundamental laws of physics.
That's a great way to put it. And who knows what other secrets these neutrinos might unlock in the future. It's a pretty exciting time to be studying this stuff.
So last time we were talking about how supernovae aren't these perfectly symmetrical explosions. And you mentioned this thing called SASI.
Right, SASI, Standing Accretion Shock Instability. It's kind of a mouthful, but it's a really cool phenomenon.
Yeah, you were about to explain what it is.
Okay, so remember we were talking about how sometimes the shock wave from the core collapse can stall out. It's like it hits a wall and can't push through.
Yeah.
Well, SASI is basically what happens when that shock wave starts to, like, slosh around. It oscillates.
Okay, so the shock wave stalls, and then it's like, wait, how do I get this explosion going again? And it starts, like, bouncing back and forth.
Yeah, you could think of it that way. And scientists think these oscillations are actually crucial in reviving the explosion. They give it the extra push it needs to really get going.
So it's not just a one-and-done explosion. There's this whole back-and-forth thing happening.
It's way more dynamic than we thought. And the cool thing is, those oscillations, they create these fluctuations in the neutrino signal. And detectors like IceCube, which is super sensitive and buried deep in the Antarctic ice, it can pick up on those changes.
Detecting these tiny variations in neutrinos from an exploding star, probably thousands of light years away. Pretty mind-blowing.
It's really incredible, and it shows just how powerful these detectors are. But even with all of this, all of the amazing tech and these powerful tools like CENU-WPY, there are still some big questions out there, things we're still trying to figure out.
Like what? Give me an example. What's got you stumped?
Well, take turbulence, for example. Remember how we were talking about how chaotic it is inside a supernova? Well, all that turbulence, it affects how neutrinos oscillate. But we're still trying to figure out exactly how. Like, can we model it accurately enough to really understand what the neutrinos are telling us?
It's like trying to have a conversation at a rock concert. There's so much going on, it's hard to make out what someone's saying.
Exactly. And then there's this other thing, something called ELISA, lepton emission, self-sustained asymmetry. It's a mouthful, I know.
ELISA. Okay, what is that?
So we talked about how supernovae aren't perfectly symmetrical, right? ELISA basically means that certain regions of the supernova might actually be spitting out more neutrinos than others.
Okay, so it's not just that the shape of the explosion is uneven, but certain parts are like, here, have a bunch of extra neutrinos. Why does that happen?
Honestly, we're still trying to figure that out. It's one of the big mysteries. It could have something to do with how the explosion itself happens, or maybe even how heavy elements are created in the process.
So we've got turbulence, we've got this ELISA phenomenon. Anything else on the supernova neutrino mystery list?
Well, there's this whole other realm of possibilities, physics beyond the standard model.
Okay, now we're going full-on cosmic. The standard model. That's like the rule book for how particles and forces work in the universe, right?
Right. It's like the foundation of our understanding of physics. But there are some things it can't explain, like dark matter, dark energy. And some scientists believe that supernovae could hold clues to these bigger mysteries.
So these exploding stars could rewrite the physics textbooks.
It's definitely a possibility. Who knows? Maybe they hold the key to understanding these fundamental forces that we can't even see. And with every new supernova we observe, with every neutrino we detect, we get a little bit closer to unlocking those secrets.
I am just like floored by all of this. It's incredible to think that something as seemingly insignificant as a neutrino could hold the answers to some of the biggest questions in the universe.
Right. And to think, just a few decades ago, we barely knew anything about these particles. It's really exciting to think about what we might discover next.
It really is. This whole deep dive into the world of supernova neutrinos has been incredible. Thanks so much for guiding us through it all.
Anytime. It's been fun.